In this first video on using accumulation formulas, we'll talk about the building blocks. That is, we'll look at some simple formulas of definite integrals that we'll know how to calculate exactly. In later videos, we'll look at how to put those pieces together to find integrals of more complicated formulas. Until we learn about the fundamental theorem of calculus, the collection of definite integrals that we'll find formulas for is pretty limited. So we're going to start with these power functions. That will be our first example, and we'll look at how we can find those. We're going to adopt a philosophy for this video of motivating all of these using area rather than doing Riemann sums. And so as we talk about these definite integrals, we'll motivate it through the idea of signed area. So we're going to be looking at integrals of functions that are powers of our independent variable, or our integration variable. So we're starting with these functions that are x to some power. Our accumulation functions, we're going to always, for these powers, start at x equals 0 and see what happens as I go to any arbitrary endpoint. Because my endpoint here is x, I need to change my variable of integration. I'll use z for this video. For our first power that we're going to consider is the power 0, and so x to the 0 is 1, and so our integral is the integral of 1 dz, and that's often written as just the integral dz, so we're calculating the same thing as if we did an integral of just dz. So if I think about the area interpretation of a definite integral, we're looking at a function that has a value of 1 for all values of x. And the definite integral we're looking at is starting at x equals 0, and it's going to some arbitrary value x. With a height of 1, we can easily calculate the area of that integral, or area of that rectangle. And so we've got a height of 1, a width of x, and so this area is x. And that gives me my first definite integral. What we found then is if I do an integral starting at 0 and going to some endpoint, the integral of 1 dz is equal to the value of that upper endpoint, so x. If I were to change the height of this graph, and instead of be at at height 1, and instead have any height, that would correspond to an integral from 0 to x of my constant dz. And now my rectangle has a height of c and a width of x. And so that formula would be c times x, where again, x is the end value of my integral. We now look at our second example. Here our power is 1, and so we're doing an integral again starting at 0, ending at my endpoint x, and now it's the integral of z dz. So what's the function that we're using for our rate in the integral? Well, it's y equals z, or y equals x. And so I graph that function, and again we start our integral from z equals 0 up to some value that we're labeling x, and I'm interested in the definite integral is the area of now a triangle. So when p is 1, my area is a triangle, and so this area is 1/2 the base, which is x, times the height. Now because the y equals z, the height at that edge is also x, so it's 1/2 x squared. So by geometric ideas, this integral has a value of 1/2 times my endpoint squared. So wherever I end my integral, I square that endpoint and multiply by 1/2. Our third example of an accumulation function that we'll develop uses the power of 2, so that I'm integrating my independent variable squared, so z squared dz, again going from 0 to 2. When I draw the graph of this function, we know that y equals z squared is a parabola. So here's y equals z squared. And our integral, we start at 0 and go to some end value, which we're calling x. And the idea of the definite integral is we want to find the area of that area under the parabola. Right, so we don't have a good quick geometric sense of how to do that. With Riemann sums we can find a formula, but I wanted to point out that even as far back as 2200 years ago, the Greek mathematician Archimedes came up with a strategy. Now technically Archimedes' approach was looking at area inside of the parabola, so he might have been looking at the area that's inside, and his strategy involved taking triangles inside and calculating the area of a triangle, and then using triangles inside the remaining piece, and repeating this process over and over again until he exhausted all the space inside of that triangle. So there was this limiting idea that he went to infinity. And so Archimedes really looked ahead at some of the ideas of calculus. For us, the geometric consequence of Archimedes' result is that if I thought about the area going from 0 to x, below the parabola, it'll be 1/3 of the endpoint cubed. So that's Archimedes' result, 1/3 x cubed. And we start to recognize that a pattern's developing. First, let's look at the power where we start. Inside the integral, I have a power 0. Its accumulation formula has a power 1. When the integral has a power 1 inside, the accumulation has a power 2. When the power is 2 inside, my accumulation has a power 3. Next, if I think about the constant that's multiplied in front, notice that when p is 2, so that my accumulation has power 3, I multiply by 1/3. When my accumulation has power 2, I multiply by 1/2. When I look at this first term, when the power is 1 on the accumulation, it looks like there's no constant. Well, that constant is 1. It appears that there's a pattern that the integral, if I have a power, any power of z inside the integral, that the accumulation is going to be the reciprocal of 1 higher than the power, and the x, the endpoint, is raised to the p plus 1 power. So we saw that Archimedes was able to show that back in Greece for p equals 2. An Arab mathematician named Ibn al-Haytham was able to show that this was true for powers 3 and 4. So that was quite a feat. And the higher the value p, the more complicated it became. And so it really wasn't until we had the Fundamental Theorem of Calculus that we were able to show that this rule actually works for any power of p, with one exception. We're never allowed to do p equals -1. So p can never equal -1. And you should see that if you tried p equals -1, we'd be dividing by 0. Let's look at some examples now. For our first example, we want to look at an integral. I start at 0 and I go to 4 of the function x squared dx. Now you'll remember that our accumulation formula is we were using the variable z, but when I have constants in my integration, it doesn't matter what variable I use. This is the same as if I had written the integral, same limit, 0 to 4 of the function z squared dz, or any other integral that we want. Our rule for this integral that we found earlier is I look at the power, so here the power is 2, and so I'm going to have a value, 2 plus 1 is 3, so it's 1/3, and we'll use the endpoint cubed, so times 4 cubed, which gives me a value of 64 thirds. For our second value, again we're integrating x squared dx, but notice that now I'm starting at 1. We found an accumulation formula for x squared. That was 1/3 x cubed, and we've learned that the integral is the change in the accumulation. So we're going to have the accumulation evaluated at the endpoint 4 minus the accumulation formula evaluated at 1. Just to remind you of what that context means, the accumulation at 4 is the integral from 0 to 4 of x squared dx, and the accumulation at 1 is the integral from 0 to 1 of x squared dx. So this is actually just an application of the splitting rule. Well, now let's use our formula. The accumulation, if I use an endpoint of 4, will be the 1/3 endpoint cubed, and evaluated at 1 it'll be 1/3 1 cubed. So we have 64 thirds minus 1/3, that's 63 thirds, or 21. For our third example, we have a power of 3, so my accumulation function that we're working with in this example will be the 1/4 x to the 4th, and this definite integral will be the value of that accumulation at 3 minus the value at the starting point, -2. So we'll have 1/4 of 3 to the 4th minus 1/4 of -2 to the 4th. So that gives me 81/4 minus 16/4. Notice that this negative raised to an even power is positive, so that I get a net 81 minus 16 is 65/4.